Hi friends, let's have a look at problem 2044. Count number of maximum bitwise OR subsets. This is today's daily challenge problem. So we are going to give a detailed analysis on solutions to this problem. So in this video, I'm going to focus on two methods. One is bitmask, the other is backtracking. So these two methods are very basic and very fundamental. It's actually very beneficial if you master these two algorithms or two strategies to solve problem. So here we are given a string called nums. So we want to find the maximum possible bitwise OR of a subset of nums and return the number of different non-empty subsets with the maximum bitwise OR. So this problem actually is very special because what we are considering is bitwise OR. So if you because here we are considering positive integers, right? So here the length of this array is bounded above by 16. So if we consider consider the length of this nums, let's call it n, right? Then for each element you can choose, or you can or not. Then the possible ways of getting the number of ways of subarrays, or here we call it subset, is this, including the empty one. But if you minus 1 using this number, you are going to get all the non-empty ones, right? So due to the constraint here, so we can find specifically all the subsets or the subsequence for this problem. So that's the first observation. We can find all the possible subsets. So here actually it means subsequences, right? So this is one thing. Another thing is that the bitwise OR bitwise OR of the whole nums array is maximal, right? The reason is we are considering bitwise OR because bitwise OR for each number. So if you have 1 and 0, or 1 and 1, or 0 and 1, you are going to get 1, and then only 0, 0, you get 0, right? So because if you do exclusive OR, and the more, so you will not decrease, right? Just become increasing, though maybe not strictly, right? So for example, this one, the exclusive OR will always be true, right? And then because if you exclude more 2's, it will not change the maximum exclusive OR. But here, for this special example, so these all the subsequences will be good. So here we have 2 to the power 3, that is 8 subsequences, but there's an empty one, so minus that one, you are going to get 7, right? So now with that said, we can do our first one, so which is bitmask. This is very straightforward. First, let's get the maximum bitwise OR, right? So let's call it target, right? So then we just do a for loop. So for y in nums, so we're going to target OR because y. Then this way, after this for loop, we are going to get the maximum exclusive OR for this array. Then our task will be find the possible subsequences that have this same exclusive OR. So this will be here. Another comment is that if you don't want to use this for loop, you can use the reduce function, right, to get the exclusive OR for all the for the sequence or for the array. So now let's use bitmask to do the counting. So because there are 2 to the power n possibilities, including the empty one. So we are going to do something like this. Let's call it result. It's a counting variable. We are going to return its final state. Then for mask, I just call it mask in range. So to the power n, right? This is the 1 shift left n units. Then for each of this number, then if we look at its binary representation, it corresponds to zeros and ones. For example, we have for the first example, so if we have 0, 1, it means we choose the first one and not the second one. If we have 1, 0, we are going to choose the second one. If we have 1, 1, we are going to choose the 2, right? So this is the same. So now we want to do this. So first temp, so we're going to set it to be a 0. Then we are going to compute the corresponding subsequence not exclusive, the bitwise OR result, right? So for this, so we want to check if the position, at position I, so the element in nums is chosen or not. So basically for I in range m, right? So what we are going to do is if mask, and so let me check this bit, right? This bit. So if this is a 1, it means that in this subsequence corresponding to the current state temp, then nums I is chosen. So if it's chosen, so we can update this temp variable by nums I, right? So then what we are going to check is if temp equals target, right? Then we are going to increment the counting variable by 1. And then finally, we just need to return the result variable. So let's do a test. Has no attribute count max set. So here, let's change this to correct signature. And let's also write n equals length of nums. Yeah, it passes one example. We can do a test for all. It passes all the cases. But I would say here we are using some brute force to get all the possibilities. So this is the one practice. Now let's move to the second idea. So we're going to use backtracking. So here for practice, I'll first find all possible subsequences or subsets here, right? So for this purpose, first we can copy this part, right? So in other words, we get the maximum possible bitwise OR. And then what I'm going to do is I'm going to use a result variable. So this is going to hold the possible subsequence. And the solution is used to construct the possible subsequence. So notice that here there's a single form. This is a plural form. And now let's define a function. Let's call it DFS. So this is essentially recursive backtracking. First, here I is indexed, right? So we want to check from beginning up to the last index n-1. So to determine if choose this one or not, right? So here, if I equals m, right, means that we scan all the sequence. In this case, so what we are going to do is we're going to result append. So we're going to append a copy of this constructor hyper. So now we're just a return. So this is what base case, or we call it bounding, right? So next, so we are going to decide if we want to use choose nums I or not. Let's see. We first choose nums I, right? So in this case, we are going to do nums I, add to this, and then we are going to do backtracking up to next index. So afterwards, so we are going to return to a previous state. So we are going to pop, right? So this is we choose to use nums I. Otherwise, so we can choose not to use nums I. So in this case, we can directly call dfs I plus 1. So this will be our main function for the backtracking. So let's call it. Let's make a remark. Backtracking here. So then if we call this function dfs 0, then we are going to modify this result list. So we can do a print so that we know we get the correct. Let's first return 0. So because this requires return 0. Let's do a test. For example 1, because here we have 2 elements, so we need to have 4 subsequences. So if for this one you're going to get 8, so for this one we are going to get 16. Let's test this one. So you get 16, right? So now we just need a filter, right? So we can do like this. Let's see. Maybe we can write a hyper function. Let's see. Define array all. So given an array, and then let's see, answer equals 0. Then for y in array, answer bitwise all equals this y, and then return answer. Then what we are going to do here is set a result equals 0, and then we scan the result list. So for array in result, if array or array equals target, then we are going to not result in count. Let's see. So we are going to do in count increment by 1, and then what we are going to return is in count, right? So this is another way, but here for the purpose of practicing, so we do a backtracking. We get all the subsequences, and then we do filtering, right? So it passes all the cases, but this method is not very effective in the sense, because here we do a filter. So next we want to write another backtracking solution. I'm going to modify this one. So I'm going to call this one version v2, right? So let's see. This v2. So we call this let's see. Restore that. So I'm going to keep this part unchanged. And then what I'm going to do is that besides we get all the possible subsequences, I can simultaneously do a count, right? So in other words, I don't need this this one. I don't want to generate all of those. So what I want to do is I add another one. It's current. So it's the current. If we choose I or not choose I, the current bitwise OR result. So then we are going to slightly change the code. So here, if I equals n, right? So in this case, so we do another check. So what we want to check, if current equals target. Then in this case, we are going to. So here we have we can do a in count. Let's see. Equals 0. Then we can first make it non-local, right? So in count. Then here, if this condition met, so we're going to increment this in count by 1. Then we return. And here, what we are going to do is that if we let's see, if we choose nums I, so what we are going to do is dfs I plus 1. Then the current equals the previous current. Let's see, current bitwise OR with nums I, right? If we do not choose current, then current just equals current, right? So this way, if we do backtracking here, so we just start from 0, then we can directly return the in count, right? This is the slightly better than the second version. Let's do a test, right? Yeah, it passes the third example. Now let's look at the generic case. It passes all the cases and also slightly faster. So here I want to mention another detail. So let me copy this part. So I'm going to call this one v3. So here, if you don't want to use this non-local, because here this one is you cannot directly modify this, right? So you can do something like this. You can use a list and use this one, because if you use list, you can modify. You don't need this non-local thing. And then here you change this to be in 0, right? Then what we are going to return is here, right? So now we didn't use the non-local keywords. Let's do a test. Yeah, it passes all the cases. So I guess for now, so we actually presented 2 methods to solve this problem. One is bitmask, and the other is backtracking. I would say here both the 2 ways to solve this problem is sort of brute force. In other words, we find all the possibilities and then do filtering, but the formats are slightly different. Meanwhile, for backtracking, we presented slightly different formats. So this is actually very interesting to tweak and tune to digest some details. So with that said, I guess that's about it for the current video. Thank you.